Hello, in today's video we're going to explore a fundamental trigonometric function, the tangent function. This is a key concept in AP Precalculus. By the end of this lesson, you will be able to construct and describe the tangent function using the unit circle, identify its key characteristics, and describe how to transform its graph. So, what exactly is the tangent function? We'll start by building our understanding from the ground up using the unit circle. Our first goal is to construct the tangent function using the unit circle. This will give us a geometric understanding of what the tangent function represents. We'll be focusing on how to construct a representation of the tangent function using the unit circle. Let's begin with a unit circle, which is a circle with a radius of 1, centered at the origin of a coordinate plane. Now, let's consider an angle which we'll call theta in standard position. This means its vertex is at the origin, and its initial side lies along the positive x-axis. The terminal side of the angle will intersect the unit circle at a point, let's call it P. The coordinates of this point P are cosine theta for the x value and sine theta for the y value. In other words, P is cos theta, sine theta. Now, here is the key insight for the tangent function. The tangent of an angle is defined as the slope of its terminal ray. That's right, tan theta is the slope of this line. So, we can say that the tangent function, f of theta, which is tangent of theta, is equal to the slope of the terminal ray of the angle theta. Let's remember how we find the slope of a line. We use the formula rise over run, or the change in y divided by the change in x. Our line passes through the origin, 0, 0, and the point P, which is cos theta, sine theta. So, the slope, tangent of theta, is the change in y, which is sine theta minus 0, divided by the change in x, which is cosine theta minus 0. This simplifies to tangent of theta equals sine of theta over cosine of theta. This gives us a second, very important definition. Tangent of theta is equal to sine of theta divided by cosine of theta. This relationship is true as long as cosine of theta is not 0, because we can't divide by 0. So, to recap, tan thought is the slope of the terminal ray, and it's calculated as sine thought togethers. Now let's use what we've learned to describe the key characteristics of the tangent function. We'll start with its periodic behavior. Our objective now is to describe the key characteristics of the tangent function. Let's look at the unit circle again. Consider an angle theta and another angle theta plus pi. These are angles that are separated by half a revolution. What do you notice about their terminal rays? They are diametrically opposite to each other, forming a straight line. This means they are collinear. Because the terminal rays of theta and theta plus pi are collinear, they have the exact same slope. Since the tangent function is defined as the slope of the terminal ray, the tangent of theta must be equal to the tangent of theta plus pi. This identity, tangent of theta equals tangent of theta plus pi, shows us that the tangent function has a period of pi. The slope values repeat every half revolution, or every pi radians. This period of pi is different from sine and cosine, which have a period of 2 pi. This means that the entire pattern of the tangent function's graph repeats itself every pi units on the horizontal axis. Next, let's discuss another key characteristic, its asymptotic behavior. We've established that tan theta equals sine theta cos theta. The tangent function has periodic asymptotic behavior. This happens whenever its denominator, cosine of theta, is equal to 0. When does cosine of theta equal 0? On the unit circle, the x-coordinate is 0 at the top and bottom of the circle. This occurs at angles of pi over 2, 3 pi over 2, 5 pi over 2, and so on. In general, this happens at pi over 2 plus k times pi, where k is any integer. We can write this more compactly as the set of all vertical asymptotes is at pi over 2 plus k pi. At these values, the slope of the terminal ray is undefined because the ray is perfectly vertical. The graph of the tangent function will approach these vertical lines but never touch them. Now let's bring these pieces together to sketch the graph of y equals tangent theta. We know the period is pi, and the asymptotes are at pi over 2 plus k times pi. Let's sketch the graph of the tangent function, y equals tangent theta. Let's first plot the vertical asymptotes. There's one at x equals pi over 2, and another at x equals negative pi over 2. Notice, these are pi units apart, confirming our period. Between any two consecutive asymptotes, the function is continuous. In our case, between negative pi over 2 and positive pi over 2. The function passes through the origin, since the tangent of 0 is 0. If you calculate the slope of the terminal ray as theta approaches pi over 2 from the left, it becomes infinitely steep, approaching positive infinity. As theta approaches negative pi over 2 from the right, it approaches negative infinity. This gives us the basic shape of one cycle of the tangent function. The graph of the tangent function demonstrates a specific behavior. It is always increasing. You'll never see it go down between asymptotes. In the interval between asymptotes, the graph goes from concave down to concave up, with the origin being the point of inflection for this cycle. Because the function is periodic with a period of pi, we can simply repeat this shape every pi units to the left and right, filling out the entire graph. Now that we understand the basic graph, let's explore how we can transform it. We'll start with additive transformations. Our objective here is to describe additive and multiplicative transformations involving the tangent function. First up is a vertical translation, or shift. This is represented by the function g of theta equals tangent of theta plus d, where d is the vertical shift amount. A positive value of d shifts the graph upwards, while a negative d shifts it downwards. Let's look at an example. Let's consider the function g of theta equals tangent of theta minus 2. Here, d is negative 2. The original graph has a point of inflection at 0, 0. After the shift, this point moves down 2 units to 0, minus 2. The rest of the graph, including the asymptotes, simply moves down along with it. The shape of the curve does not change. Next is a horizontal translation, also known as a phase shift. This transformation is of the form g of theta equals tangent of theta plus c. The graph is shifted horizontally by negative c units. If c is positive, the graph shifts to the left. If c is negative, the graph shifts to the right. Again, the shape remains the same, only its position on the x-axis changes. Let's move on to multiplicative transformations, which change the size or orientation of the graph. We'll now look at multiplicative transformations involving the tangent function. First is a vertical dilation. This is represented by g of theta equals a times tangent of theta. This transformation stretches or compresses the graph vertically by a factor of a. A value of a greater than 1 makes the curve steeper. A value between 0 and 1 makes it flatter, and if a is negative, the entire graph is reflected across the x-axis. For example, compare tangent of theta to 2 times tangent of theta. The latter curve rises more quickly, making it appear steeper. Next, we have a horizontal dilation. This transformation is of the form g of theta equals tangent of b theta. The graph is compressed or stretched horizontally by a factor of 1 over b. This transformation directly impacts the period of the function. The new period, which we can call p prime, is calculated as the original period, pi, divided by the absolute value of b. So, p prime equals pi divided by the absolute value of b. A value of b greater than 1 shortens the period, compressing the graph horizontally. A value between 0 and 1 lengthens the period, stretching the graph. And if b is negative, there's a reflection over the y-axis, but the period is still pi over the absolute value of b. For instance, let's compare tangent of theta to tangent of 2 theta. The new period is pi over 2. The graph is horizontally compressed, meaning you see a full cycle in half the space. Finally, we can combine all these transformations into a single comprehensive equation. This is the general form of a transformed tangent function. Y equals a times tangent of the quantity b times theta plus c, all plus d. Each of the parameters, a, b, c, and d, controls a specific transformation, and they act independently. Parameter d controls the vertical shift, parameter c controls the horizontal or phase shift by negative c units. Parameter a controls the vertical stretch or reflection. And finally, parameter b controls the period change, making it pi divided by the absolute value of b. Understanding these individual effects is crucial for analyzing and sketching any tangent function, no matter how complex the transformation. Let's summarize what we learned today. We started with our first objective, which was to construct the tangent function. We learned that the tangent of an angle is the slope of its terminal ray on the unit circle. This leads directly to the analytical definition: tangent of theta equals sine of theta over cosine of theta. Then we described the key characteristics of the function. We saw that the tangent function has a period of pi and exhibits periodic asymptotic behavior at pi over 2 plus k pi, wherever the cosine is 0. Finally, we explored how to transform the graph. We learned how to analyze the effects of a vertical shift E, a phase shift of negative c units, a vertical dilation A, and a change in period controlled by B. Understanding these concepts will be vital as you continue your study of trigonometry and prepare for the AP Precalculus exam. Thank you for watching.